Okay, this is a worksheet we did on Coulomb's law, the electrostatic force this week. I'm doing a video of it because a lot of people were out that day due to the weather challenges we had this week. So I'm going to post this key as well. The first part of the worksheet, the first side, we did a simulation in FET. This is the link. I can't show you the simulation because I don't know how to switch between the camera that's right here and the computer. So I went ahead and just wrote all the numbers down. If you wanted to check it out, you can use this link to do that. But it really just shows our electrostatic force equation. Remember, that's a constant, which we don't really care about, times our two different charge values, charge 1 and charge 2. Q is our symbol for charge. And then that's divided by the distance between them squared. Okay. So we're trying to understand what relationship does charge amount and does the distance between the charges have with electrostatic force. Those are the two things you can manipulate in the simulation, and they're the two things that are going to change this electrostatic force value. Because again, this K is just a constant number. It's always the same number. So in the first part of the simulation, we changed our charge values. We had two charges that were a distance apart. They're kept the same distance apart. And then we varied their charge values. So our largest charge value was 16. This is microcoulombs, which are the units. You don't really need to worry about those. And we can see from the simulation, if we look at the force of one charge on another, that force value is the largest here. So my largest charge amount has my largest force value of 360 newtons. And then my smallest charge amount of 10 has my smallest force value, 90 newtons. And this is a force that's acts whether you're attracting or repelling. Okay, whether your charged objects want to move towards each other or they want to move away from each other, it's still a force that's acting. So that's what these negative and positive values mean. Okay. Then we looked at distance. So now we're keeping all of our charge values the same. So all of these are minus 10, all of these are plus 10. And then we changed their locations. So we had them 2 centimeters apart. Our force is 2,247 newtons. Then we moved them another 2 centimeters from that. Our force dropped to 562 newtons. And then we moved them out another 4 centimeters and it dropped to 140. So we definitely see that if our distance between our charges increases, then that's going to cause our force value to go down. If they're farther apart from each other, they can't exert as much force on each other. So, summary, the electrostatic force increases as our total amount of charge increases, and our electrostatic force decreases as the distance increases. Okay. Another thing we talked about is comparing the electrostatic force to the force of gravity. We looked back at our force of gravity equation from last semester. So I'm going to write, I'm going to write our electrostatic force equation just so we have it handy. And then we also looked back at our force of gravity. This was Newton's universal law of gravitation, where we've got another different constant, again, not one that you need to memorize or even really use, times mass 1 times mass 2 divided by the distance between them squared. And you can see, looking at these two equations, that they're really similar. Okay. There's some big differences between the electrostatic force and the force of gravity. We already said with electrostatic force, we can either attract or we can repel, depending on whether we've got like a positively charged and a negatively charged object, they're going to attract each other. Whereas if they're the same charge, they're going to repel. Gravity's always attractive. Everything that has mass is attracted to everything else that has mass. Another big difference between these two is strength. Okay, so we looked at that list of fundamental forces. We had our nuclear forces that keep all of our protons in the nucleus and keep our atom together. And then we had the electrostatic force, and then we had gravity. So, electrostatic force is a stronger force than gravity. Gravity is relatively weak. And when I say relatively, I mean it's a strong force if you're a really huge object, like a planet. Okay, but if you're just like two of us standing around in our classroom, yes, we both have mass. Yes, we're going to attract to each other, but the force is so weak that we're not going to see anything happen. So, the big similarity between these two, and I've already kind of mentioned this, is the equation relationships here, because in both cases, as distance increases, my force is going to decrease. So in both cases, distance and force have an inverse square relationship. An inverse square just means I'm dividing by the distance between them, and that's a squared factor. Okay. That means that as distance increases, my force is going to decrease. And that's the same in both cases. My two charges, the electrostatic force they exert on each other is going to be less as the distance increases. My two masses are going to have less gravitational force on each other as their distance increases. Okay. These models, I talked about these because a lot of times they like to put these on exams, like interims, for example. And we're going to add some arrows just to remind ourselves about the direction of the force. So with gravitational, we've got an attractive force always. Those two objects with mass are attracted to each other. With electrostatic, we can have attract if we're opposites. So I got positive, negative here. Or we can have repel if we're like. These two positives are going to repel each other. They don't want to be near each other. And then the last thing we talked about was this factor of change, or rule of ones. We did this last semester with gravitational law. So this is where we set everything equal to 1, and then we change the factor that's changing. In the case of this example, the distance decreases by 1/2. We see what happens to our force value. This is a way we look at these equations without having to actually use real numbers in them, because the constants have a lot of scientific notation and they're just a pain to use. And really what we want to understand is the relationships of the variables. So let's say everything's equal to 1. So both my charges equal 1, my distance equals 1. That means my force equals 1. Now I'm going to cut my distance in half. So my two charges, maybe they were this far apart, and now they're this far apart. That's a little less than half, but I think you get what I mean. So I'm going to put those into the same equation. So I've got, let's go back to our equation real quick. So I'm going to have charge 1 times charge 2 divided by d squared. I don't have to use that constant because it's the same no matter what my situation is. So it doesn't matter. So I'm going to have Q1 is 1 times Q2 is 1 divided by 1/2. That's how my distance changed. And I have to square that. So that's going to be 1 divided by 1/4. And then if I multiply by the reciprocal, so I can get rid of this fraction in the bottom, I end up with 4. Okay, so if my distance decreases by 1/2, my force is going to increase by a factor of 4. It's going to be quadrupled because I'm bringing these closer together. They can have more force exerted on each other. Another example, how much does the force change if both of the charges double? So again, going back to everything equals 1 to start with. And now both of my charges are doubled. So I'm going to have electrostatic force equals 2 times 2 divided by 1 squared. I didn't change the distance. So we actually get the same answer here. Our force is going to increase by a factor of 4 because both of my charges doubled. So if charge increases, force increases. Here we saw that distance decreased, so force increased. And then my last example, I've got 2 charges that are separated by 1 meter, and then we're going to triple that to 3 meters. So again, everything equals 1. Then we're changing distance to 3. So we're basically tripling distance, okay? So then we're going to have our electrostatic force equals 1 times 1, because I didn't do anything to my charges. All I'm doing is changing the distance. That's going to be 3 on the bottom, and that's squared. So I got 1 over 3. 3 squared is 9, so I've got 1/9. So my force is going to drop by a factor of 1/9 if I triple my distance between my charges. Again, that's just going back to what we said on the first side, that if my distance increases, my force value is going to decrease. And in this case, it's decreasing by a factor of 1/9. I'm going to post this key as well. Hopefully this will help those of you who are out. And if you were here, maybe this will help explain anything or help you refresh for the test that we have next week, which is on the 25th.